Hello. Now, continuing our work with lines and circles, we're actually going to look at the intersection of two circles, which I've called S1 and S2. S2 is the circle we've already dealt with. S1 is the circle given by this equation here. So I recognize that S2 is in the expanded form of the circle equation, but this equation here is in the other version. This is in the form x minus h to be squared plus y minus k to be squared is equal to r squared. So if I want to find out the information about this circle here for drawing a sketch of it, or in most exam questions I'm going to need this information anyway, the center and the radius are the core pieces of information about a circle that we pretty much always need. What can I read off here? Well, I can read off that the radius squared is equal to 10. So the radius is going to be equal to root 10. I don't need to worry about plus or minus because this is a length and I don't deal with minus lengths. And I know the center is going to be at h and k. So the center of S1 is going to be at h and k. That's going to be at, there's a minus in the formula here, so that means that h is 6. There's nothing added or subtracted to the y squared here. What does that tell me? It tells me that k is 0. So I now know my two pieces of information about my circles. I know the center and the radius of each circle. I have found the center and the radius of both circles. This enables me to draw a sketch, and that's going to help me for figuring out what I need to do. But if I'm looking for the intersection of two things, I'm going to do simultaneous equations. I know this already, but the sketch helps me build intuition, and it's extremely important from that point of view. So I have my sketches that I'm going to go with now. So I have the center of one of my circles is at 6, 0, and the radius is root 10, which is very approximately, for sketching purposes, 3, just so I can draw a picture of it. So I have my circle with a center of -3 and a radius of 5. I have one circle that looks roughly like this. That's my S2. And I have another circle centered up here. So I have 1, 2, 3, 4, 5, 6. So that is my center of S1, and it has a radius of around 3. So that's going to bring me back to here. So I have that circle looks something approximately like that. So what I'm looking for are these 2 points, the points of intersection of my 2 circles. So I know very approximately what their values ought to be based on my sketch. And we can also see that we are going to likely get 2 points of intersection in this case. It's not likely to be a tangent because of the way that we've drawn our sketch. Even a very crude sketch like that gives us an intuition as to what we're going to end up with. Now, the result we're going to get when we try to do simultaneous equations is a little bit surprising. We're going to end up with what's called a common chord, the equation of a line that goes through these 2 points. And then we're going to use that equation of the line to find the intersection between that line and one of our circles. But we'll come to that in a moment. So we now have our sketch done, and we know that we're doing simultaneous equations because we're asked about intersection. So let's do our simultaneous equations. We have our S1 is equal to x minus 6 to be squared plus y squared is equal to 10. Now, this is not in a form that it is particularly useful for doing simultaneous equations with two circles. We're not able to do a substitution here, or at least doing a substitution here would be quite complicated. We could theoretically actually isolate the y here, but it would be a lot of work and very likely to make a mistake. So what we actually do is go back to our subtraction method when we have two quadratic equations. So let's do that. Here we're going to square this out. Square the first by the second and double it. Square the second. Plus y squared is equal to 10. Let's reorganize this into the same format as our other circle equation, as S2, so that it's easier to do our simultaneous equations. If they're both organized in the same fashion, it's easier to keep track of things. So therefore x squared plus y squared minus 12x plus 26 is equal to 0. This is now my equation for S1, and it's in the same general shape as my equation for S2, so they're easier to take away from each other. So if I have S2 now, it's x squared plus y squared plus 6y minus 16 is equal to 0. And I'm going to subtract these two things away from each other. So again, we're back with circles intersecting. We're back to dealing with our situation where we subtract the two equations away from each other, and we can immediately see that because the circle equations always have x squared plus y squared by themselves in front, they're going to sum to 0, and we'll be left with a linear equation in x and y. And we're going to use that to find our points of intersection. So if I subtract S1 away, I'm going to end up with minus x squared minus y squared minus 6 plus 16. So I end up with 0 plus 0. Write that in. So S1 minus S2 ends up being minus 12x minus 6y plus 42. And I recognize that if I have a common factor of 6 here, so I'm going to divide both sides actually by minus 6, so I end up with x and y being positive. So divide by minus 6, and I must divide the other side by minus 6 as well. It won't have any effect because it's 0, but for keeping balance we must do it to both sides. 2x plus y minus 7 is equal to 0. I now have a linear equation, and in point of fact what I've got, call this L, what I've got is the equation of the line that goes between the 2 points that I want. So this is the equation of L. And what I'm now going to do is just get the intersection between L and either of my circle equations. So which circle equation is easier to get? Well, I want to avoid fractions if I possibly can, so I want to isolate y. So what has an easier thing to substitute in for y? S1 does. Here I have, for S1, I just have a y squared to sub in. Here I'd have a y squared and a y to sub in, so there'd be more work. I'd be more likely to make a mistake. So I'm going to try and sub in L. I'm going to look for the intersection of L and S1 because rearranging this is easier for y. So I end up with y is equal to minus 2x minus 7. Sorry, plus 7. I can sub that in, and I only have one substitution to do for S1. I'd have two substitutions to do for S2, which is more complicated algebra. So to make life easier for myself, I'm going to sub into S1. You'll get the right answer either way. Subbing into either of my circle equations will give me the right answer. But I want to make the algebra as easy for myself as possible. if I can. So I have my L here, and I'm going to rewrite down S1 in its expanded out version, because it'll be easier for me to work with. X squared minus 12x plus x squared plus y squared. I'm looking for my circle equation here. X squared plus y squared minus 12x plus 26 is equal to 0. I'm now going to sub in my y value here and solve for x. That's 2x. This is exactly the same as finding the intersection between the line and the circle. There is nothing that we haven't already seen before in what I'm about to do. So we square that out and tidy it up a little bit, and we will end up with 5x squared minus 40x plus 75 is equal to 0. Recognizing that I have a common factor of 5 here, divide both sides by 5, and I end up with x squared minus 8x plus 15 is equal to 0. Solving this, I will end up with x is equal to 3 and x is equal to 5. So we know how to solve this. It's just solving a quadratic, which you already know how to do. So x is equal to 3 and x is equal to 5 will be your solutions. But we're looking for coordinates of points. Therefore, we must go back to our line equation. Y is equal to minus 2x plus 7. Y is equal to minus 2x plus 7. Sub into that equation, and we get y is equal to 1 and y is equal to minus 3. So my points of intersection are at 3, 1 and at 5, minus 3. And I can see from my drawing that that is very roughly correct. I didn't end up with things in the wrong quadrant or anything like that. So my sketch again helps me to build intuition as to what I would expect to see for an answer. Now, one point to bring up is I ended up being able to solve this quadratic and get my points of intersection. If I wasn't able to solve this quadratic, if I ended up with a quadratic that didn't have real roots, that would tell me, if I didn't get a proper solution to this, it would tell me that my lines do not cross each other. So if I didn't get a solution to this, if when I tried to use the minus b formula, I ended up with complex roots or imaginary roots, that would tell me the circles didn't cross. And if I got repeated roots, that would tell me that I had a tangent. Why would it tell me that? Because it would mean that my line here only touched either of the circles at one point. So that would mean that I had a common tangent. My line L wouldn't be a chord. It wouldn't be going through 2 points. It would be a common tangent. So the situation we've got here for L would be called a common tangent. Sorry, it would be called a common chord, I should say. And if we only got one point of contact, then L would be called a common tangent, because it would be the tangent common to both circles. And that's what we need for the intersection of circles.